So could it ever be the right thing to expand a node with higher f cost than the minimum f on open?
Because in that specific situation, if they had done that, they would have just raised the destination right away.
In any particular situation, we can, in a grid planning problem, you can always just look and say that's where it's supposed to go, and that would be optimal because you are solving the problem. Now, in a simple situation like this, you might be willing to guarantee that you're going to find the optimal path, but it actually doesn't, the problem doesn't have to get too complicated before you really have no idea what the optimal path is. So this is a very simple world. The reason this algorithm is having so much trouble is its heuristic is underestimating significantly. So if let's say, so it's a grid world that agent is in. So, and it's using Euclidean distance as the heuristic. But Euclidean distance is actually not the very best you could do. I mean, if you're trying to go from here to here, for example, if you can only move 8 ways on the grid, you're going to have to go here and then there, whereas Euclidean distance is going to be that distance there, which is smaller. So that's why that agent is expanding so many states. And I think they also have the tiebreaking screwed up. Anyway, this is the search with the correct heuristic. And the correct heuristic for this kind of domain is called octile distance. And it takes into account the fact that you can only go diagonally. So octile distance is actually perfect for 8-way movement as long as there are no obstacles. So if you compute octile distance to your goal, as long as there's nothing in the way, the heuristic is exact. It gives you the perfect answer. So that's the second video is with octile distance, but they're using the crappy tie-breaking rule. Why? If you have 2 nodes that have the same f cost, picking the one that has lower g, why is that a bad idea? Tyler.
Because the heuristic is still larger, so probably more total moves from there to get to the solution.
Yep, that's one way to think about it. That's absolutely one way to think about it. So if you've got 2 nodes that have equal f, so let's say these are the f costs. Here we've got node 1 and node 2. Let's say this is G and this is H, and this is G and this is H. This N2 just adds further to go to the goal. It's going to take longer to get there. So that's true. That's not entirely compelling, though, for the same reason as I was about to spout at Lee earlier, but somehow we got distracted. Lee, you were saying at one point it might be occasionally good to expand a node that has the non-minimal f. And in a specific case, we can see, okay, fine, that makes some sense. But in general, that's a poor strategy because, remember, A star is going to have to expand every single node whose f value meets a certain criterion. Anybody remember what it is? Remember those big circles, big gray oval? A star has to expand every node whose f value is less than the optimal solution cost. Just in order to prove that there isn't some wormhole through the 11th dimension that gets you to the goal like with 0 cost. If there were ever a node on open that costs less than the solution you're about to return, you might always have in the back of your mind, what if? You know? I don't know about you, I live in fear of those moments, I should have asked her out. Or, I should have taken that class. I didn't prove to myself that it was a bad idea. And A star is having that exact same issue. If you expand a high F node, you never know. Maybe there's a 0 cost move, takes you to the goal. So you're always going to have to expand every node that has F less than I think on the slide I had f less than f star, something like that, or maybe I had f of n less than f star of opt. A star has to, in order to guarantee optimality of the resulting solution, has to expand every node whose f is lower than the cost of the optimal solution. So you're going to have to expand a lot of those nodes anyway. Now, maybe I'll let you say it. Go ahead.
I was just wondering, is there a way of calculating the probability that unexpanded nodes, if you're one away from the solution,
Yeah.
and there's
How do you know you're one away from the solution? Anyway, leave that aside.
It's a different thing. If at the very beginning there was a fork and you took a left and you're down here, and at the fork you haven't expanded those nodes yet, but you're just about to make the solution, and maybe this would be quicker. But is there a way of factoring in the fact that this is going to have to take its own little trip down the right fork before it reaches the solution, and figure out, and that's not even taking into account the fact that I might have just solved it and saved time there instead of saving time and finding the best one.
You know, if you want to save time, A star may not be the algorithm for you, because A star is about proving optimality. And okay, fine, we all want to save time, but at the end of the day, we got to prove we were optimal. So we're going to have to expand all those nodes with f less than the cost of the optimal solution. Might as well expand them lowest first. Doesn't matter. It turns out if you expand them lowest first, you have the fewest number of duplicates. So it's a good search order. I think one of the things you were saying sounded like something that's actually research we're doing right here at UNH. If I've gone a long way here and I'm about to get to a goal, and I have an unexpanded node here with a lower f cost, this might almost be at a goal, and this might be quite a ways from a goal. Is there a way I can sort of judge, well, is it really worth going down here? What's the probability this is going to end up with a lower cost solution? That kind of stuff, that's super fancy mojo. So great final project idea. But doing that right, it's a little tricky, but people have definitely thought about it. People right here in this building have thought about it. So if A star has to expand all these nodes, mandatory, non-optional expansions, then how come I'm making such a big deal about tie-breaking here? I mean, who cares about tie-breaking? If the f is low, we're going to have to expand it. Nathan.
I thought you should break ties with the G cost. The way you said was wrong. So I tried that in my algorithm, and it improved it, but like barely. It only saved like 10 nodes out of 1,000 or something. And I got rid of it because I figured I was probably not doing it right. But why is that not a good idea?
Yeah, so the answer is all those f layers that are less than the cost of the optimal solution, we have to expand all the nodes, so it doesn't matter. But on the last layer, right, you've generated the goal. It's sitting on open somewhere. Can we please expand it now? If you have a whole bunch of nodes with equal f, the one that has the one that has an h cost of 0, like it's the goal, can we expand that one first? Let's put it at the front. It's going to, it'll have the same h, sorry, gee, I'm having a problem with my letters today. It has the same f as all the others, but it's going to have very high g, right? So this is all g, h equals 0 for the goal. So you always want to break ties by preferring to expand the nodes with high g. Because on the last layer, you're going to expand the goal first. And all these other nodes with the same f, but that are not goals, are just going to sit on open and not get expanded.
Okay, so you want to break ties with the high G. Okay.
You want to break ties on a high g, and that will lead to an improvement.
Okay.
That last f layer can be a substantial portion of your search, like easily half. So if you can make your search twice as fast just by breaking ties in a good way, absolutely you should. Now, and let me demonstrate. So this is the wonderful octile distance with bad tie breaking. Here's the wonderful octile distance with good tie breaking. Boop. It makes a big difference. So that's why Nathan made that video. Not you, but another Nathan.
So with A star, once we hit a solution where H is 0 and G equals the F that we calculated, we're done. We don't expand anything else, no matter what?
No. That node just goes in open. And the question we've been talking about is how do you sort the open list? We all know it's sorted by F. You want low F first.
Right.
We're going to expand the minimal F node. But I was just raising this question of ties. What if you have two nodes that have the same F value? Can we do anything clever about having the right one in front? And the right one to have in front is the one with the higher G and lower H. Well, okay, let me give you another way of thinking about it. If you don't like my explanation about the last layer, here's another way to think about it, which is that G is experience. You have been there. You have done that. You have experienced that path cost, that G value to that node. You've trod those paths. You have sweated that sweat. H is some illusionary fantasy, right? Oh, you're so close to the goal. Believe me, really. Right? It could be a bunch of hogwash. Like maybe somebody fed you H equals 0. I mean, for crying out loud, H could be anything as long, I mean, if you're lucky, you have an admissible heuristic, so it's optimistic, so it's less than the true value, but that's all you know. So, if anything, the H value is underestimated, so it could be greater. Typically, the error in H is proportional to the H value. So if you have a whopping huge H, typically the heuristic underestimates by a factor of 2 or something. So the true value, here's where you see my sloppy planning of my drawing. So this, the true H might be up here, where if this one's also off by a factor of 2, it's only going to be up there. So you always want to take the one with the bigger G. And this one is going to be just right there, because there's no H at all. So
maximizing G in this case feels backwards because we're trying to find the path with the smallest.
Yeah, it's true. But remember, these F's are the estimate of the cost of a solution going through that node. And they're lower bounds on the cost of the solution going through that node. And so you get a more accurate estimate if it's all true than if it's mostly made up. So that's the thinking about tie breaking. Okay, that was just a little before class interlude. We have a bunch of end of letter questions, including some that I didn't answer last time. Someone asked, how did I get into AI? And that's a great question. I think it's always been fun. I've always thought it was fun. I've always liked computer science. My first year in grad school, I played with robots, and that was once you do that, there's no going back. It's just way too fun to do anything else after that. Okay, this we're going to answer later. Have you ever solved a problem while on the toilet? And that's quite an amazing. I've never been asked that question in class before. I don't know. I've certainly had good ideas in the shower. Have I had a good one on the can? Probably. I mean, when you're thinking about something, you're thinking about it, no matter what you're doing. Okay, this is a really important question. There were a whole bunch of people asked the same question. Depth first versus breadth first search. I have really mixed feelings about depth first search. There are some reasons that depth first search is awesome. Excuse me?
If it finds a solution.
Depends on your depth bound and whether your search space is infinite. So it might not actually find a solution. In this domain, it does find a solution because it's a nice finite domain, and you're probably doing cycle checking or something nice like that. If you weren't doing cycle checking, it would basically not find a solution, even though the space is finite. What's a wonderful thing about depth first search? Yeah. You just blurt it out. Okay, so yeah, linear memory, that's great. Everyone loves linear memory. I mean, you have to have linear memory in order to just store the solution path, right? So if you can do the whole search just remembering that much, that's pretty awesome. But it's not guaranteed to be optimal. So breadth first search, or I hate breadth first search. Can we just call it uniform cost search? Uniform cost search. Why is that good?
You're guaranteed to find optimal solution.
Yeah, and why does it suck? Space, memory, yeah. You got to remember every node you've seen. And you have this huge open list that could get arbitrarily long, and yeah, the memory is terrible. So 6 to 1, half a dozen. You want a linear space, but totally non-optimal, or yeah, it's really tough. There's like no perfect search algorithm. So that's too bad. A lot of people ask questions about that. Iterative deepening. A couple people asked about iterative deepening. Why is iterative deepening lousy? Oh, this is just such a depressing part of the class right now. Why is iterative deepening so bad? This thing we just all struggled to learn.
You have to redo the search.
That's no big deal. That's no big deal, because remember, trees, don't let the things out there in the ground fool you. Trees look like this, right? Trees look like that. Right? That's the shape of a tree, okay? None of this triangle baloney that everyone's been foisting upon innocent students since the dawn of time. Trees are not triangles. They're whoosh. They're like exponential trumpets. It's crazy. So iterative deepening, re-expansion is so not an issue. You got to get that out of your mind. You got to believe the math. It's that whole doubling thing that we laboriously did. Like regenerating these layers, not a big deal, because compared with this layer you're now on, they're nothing.
And I don't know if this is just because of my algorithm sucks or whatever, but I found when using iterative deepening, if I just said, oh, try 3 first, and then the solution wasn't until 12, like I wouldn't even hit the 1 minute mark. But if I started at like 10 or 11, it got it quite quickly. So it seems to me that having to redo that much of it does kind of make a difference.
Yeah, that's an interesting observation. I'll have to think about that a little bit. Grid worlds are generally very bad for any type of depth first search, as you guys are discovering. So I would expect iterative deepening to suffer a lot, but I would also expect that the re-expansions would not be a big issue. So it's not obvious to me why you're seeing that behavior right off the bat, but Dan does.
We're supposed to keep the same closed list for each iteration, or not?
There's a line in the assignment that's really important that says your depth first search is supposed to run in linear space. If you keep a closed list, are you running in linear space? Linear in the solution depth. Yeah. So don't forget that line in the handout. Yeah.
We did talk about using a closed list to do cycle check, where you pull nodes off the closed list as you backtrack.
Well, we talked about a hash table. We didn't call it a closed list because it ain't no closed list. Did you get a haircut?
Yes.
Oh, it looks great. It's not a closed. If you're just doing cycle checking with a hash table, that's just cycle checking. A closed list, that is an honest to God, Dijkstra kind of thing. Like, you're remembering stuff. A node is closed when it has been expanded. So a closed list, the list of expanded nodes. I mean, that's huge. Whereas just keeping track of what's on your current path in a hash table in order to speed up cycle checking, that's just an implementation detail. That's not a whole different algorithm. All right, so iterative deepening. Oh, man, when are we going to hit the perfect search algorithm? How close can you get to finding an optimal solution with something that's a lot faster than A star? Oh, man. I wasn't going to talk about that. So if you want me to talk about it, ask it again. That's another end of lecture question. And better yet, at the end of the spring, my PhD student, Jordan Thayer, is going to be defending his dissertation, which is entirely on the topic of finding solutions that are pretty good, way faster than A star. So he's going to give a big talk about his research, so you guys should all come. Is it ever possible to get close to the optimal heuristic? Yes. Actually, it was AAAI. No. Ijkai. Polynomial time. Perfect heuristic. Yeah, computing perfect heuristics in polynomial time. Now, you might say, well, gee, this is significant because there are a lot of NP-complete problems that you can code up as heuristic search problems, and we all know that if you have the perfect heuristic, you just go straight to the solution. So have we just proved that P equals NP? Actually, this is computing perfect heuristics in polynomial time for some small subclass of instances. So it's not in the general case. But there's this is cutting-edge research by a very smart bunch of folks. Yeah, people are working on that heavily as we speak. Can the difference between a state and a node be summarized as the difference between a location and that location and the information needed to get there? Now, if by location you mean state, so we have a state is a state, and a node is a state plus the information needed to get there, then that's absolutely true. Absolutely true. These are basically the same question. Are there any algorithms that have been created by an AI system? And the answer is absolutely yes, and for many different definitions of the word create. So you are going to write for assignment 3 a program that creates its own heuristic functions. So that's kind of cool. But that's not the search algorithm itself, that's just the heuristic function. There have been lots of people who have written programs that have a bunch of different parts, and there's a search that searches among all different ways of putting the parts together to make a search algorithm. Some of that work goes by the name genetic programming, where you have some code and you have maybe bunches of programs and they're each sort of suck, but then if you combine them together in various ways, some of them suck less than others, and those ones get to make more copies of themselves and are then overrepresented in the population, and then when you put them together, they're more likely to have their properties represented in the new solution population. So there's a lot of work like that. So yeah, absolutely. A lot of work's been done on that. Someone thought that the star in A star was a Kleene star, and it's totally not. It's a shiny star because it's admissible. It returns optimal solutions.